All right, this is the third and last lesson reviewing some of the key ideas from Math 9. Unlike the last few lessons in which the focus was purely on solving equations, just algebraic equations, this is about using some equations and connecting it to graphs of what we call linear scenarios. Right, but again, it's all review from some core topics of Math 9. Doesn't mean it's easy. So the first question here involves this graph in which it shows the distance a bullet travels after being fired from a rifle. And if you look at the details of the graph, you see time is on the x-axis and distance in feet is on the right axis. Now this document you see here, you can access the exact same document, a blank version of it, on the Teams page, a PDF you can print, and I'll always eventually give out hard copies of these in class whenever I see you. All right? And whenever we have lessons that have graphs or a fair amount of writing, I will always give either a PDF or a hard copy of a sort of outline of it. All right, so my first question is, how fast is a bullet traveling? Well, to find how fast it's traveling, I need to essentially look at this line and pick any 2 points on this line. And so, a good point to pick is the start, 0, 0. But I pick some other point. And so I just need to look on this graph and find some place where I feel pretty confident I know the coordinates. And I'm going to pick this point right there. At that point, I know after 2 seconds, the bullet has traveled 5,000 feet. And after 0 seconds, it has traveled 0 feet. So really, all that really matters, knowing that it started at 0, is that this bullet traveled 5,000 feet in 2 seconds. And so it's not wrong to say how fast the bullet. It's not wrong to say it travels 5,000 feet every 2 seconds. It's just kind of weird. You don't usually see velocities or speed given every 2 of something. It's usually every 1, like kilometers per 1 hour or feet per second. And so for this, I just want to reduce by fraction and really just go 5,000 divided by 2. And we get 2,500 feet per second. Those units are really key, okay? Feet per second. And that's how fast the bullet's traveling. And it's always traveling at speed according to this graph, and that's because the line isn't changing direction. If this started to kind of slope down like this or something, then I know the speed is not always the same. All right, so next, write an equation that relates the distance a bullet travels to the time after being fired. Well, for this, I need to give variables to my x and y axes. And the x-axis, I'm not going to use the variable x because I want to use t for time. That's pretty standard. And I want to use d for distance, which is also very standard. It's not wrong to use x and y, but why? Why not use, in this case, d and t? And so how does distance relate to time? Well, notice what I really need is right here. This tells me, this 2,500 feet per second tells me every second the bullet travels 25 feet. So if I know the number of seconds the bullet's been in the air, I know the distance because every single second it travels 2,500 feet. And so I can express that as an equation by saying distance, or just d, equals 2,500 times time. And I'll just kind of highlight these. But literally, that equation there summarizes the graph without any pictures, any words, or anything. It's not necessarily better, but it is succinct. It's just that equation. And if you know what t and d stand for, t is time in seconds, d is feet, then this tells me exactly, this one equation, a relatively simple equation, tells me, the distance the bullet will travel after any given time. Notice if I just replace t with any number I want, 3, I know after 3 seconds the bullet should have traveled 2,500 times 3, which is 7,500, which is about what I see right here. Here's 3 seconds, and notice that looks like halfway between 5,000 and 10,000. And so this speed, this velocity, was really important for this. That number of 2,500 was the coefficient of my t here. And later on we'll use the word slope, which maybe you've learned about before. 2,500 is the slope of this line. Okay, and there's a good chance you've learned that word before from Math 9. That's it. How long does it take a bullet to travel 1 mile? Well, this question right now is not fair until I tell you how many feet are in a mile. I don't expect you to know that, but I will now tell you. There are 5,280 feet in 1 mile. Okay? The imperial system doesn't have nice round clean numbers like the metric system. So 1 mile is 5,280 feet. So really, I'm trying to find how long, right? How long is time? How many seconds does it take to travel 5,280 feet? Well, I can now take my original equation from up there and replace the d with 5,280. And I can say 5,280 equals 2,500 times the time I'm trying to figure out. I don't know what the time is, but I do know the distance is 5,280. And now I can solve this equation, a single one-step equation using the sort of principles I reviewed in the last couple of videos. So all I need to do here is divide both sides by 2,500. Right? And then I'll have isolated t. And so what is 5,280 divided by 2,500? I don't know. I'll use a calculator. And so if I use a calculator, I get about 2.1 seconds. I'll put a little dot over the equal sign to show that it's approximately. So about 2.1 seconds. So this bullet, according to this graph, according to this model, travels a full mile, 5,280 feet, in just over 2 seconds. All right. Last part for this question. The speed of sound is 1,125 feet per second. All right, so notice I can see already the speed of sound is less than the speed of a bullet. So how could I show that statement? The speed of sound is 1,125 feet per second. How can I show that on that same graph? Well, let's look up the graph. Let's think what this graph is showing. And let me clean this up a bit. This graph, remember, is showing me the distance a bullet travels over time. I want the distance that speed travels. And the key part is that I tell you that speed travels 1,125 feet per second. That means in 1 second, the speed of sound, in 1 second, a sound, let's say there's, I don't know, a firework that goes off. In 1 second, that sound from that firework has traveled 1,125 feet. Well, I can show that on the graph by finding 1 second on my graph, on my x-axis, and estimating 1,125. I'd say that'll be about right here. And I also know after 2 seconds then, it's going to be 2 times that. In 2 seconds, it's going to travel 1,125 times 2, because every 1 second it travels 1,125 feet. And so 1,125 times 2 is 2,250. So right here. And really, I can start to see this pattern where the speed of sound must form another line, but with a lesser slope. And that is how I show that green line I've sketched out quickly shows me the speed of sound. The red line that was given shows you the speed of a bullet. And so I'm now showing 2 things. Notice again, we can tell by looking at the value of the speed of sound that it was less than the speed of the bullet. And notice on the graph, the slope is less, if that word sounds familiar. All right. Last question, I think. Yep. OK, so here. This graph here doesn't relate to anything. It's not an applied problem. It's a graph with 2 points, 0,5 and 1,0. Okay? And I'm telling you these are both points on the line y equals negative 5x plus 2. X represents points on the x-axis, the horizontal axis, y is on the y-axis. All right, so the first question is find 3 more points that are on this line. Now, a few ways of doing this. One way is to use the equation. Okay, how do I do that? Well, notice, let's make sure we're clear about how the equation connects to these points. Let's look at the point 0,5. That's telling me on the graph that when the x-coordinate is 0, the y-coordinate is 5. And notice if I look at my equation, if I replace x with 0 on my equation, I get negative 5 times 0, which is 0. And so all I've left is positive 5. When x is 0, y equals positive 5. That's what that point is telling me. And I can do the same thing for any point on this line. So notice the other point I gave you, 1, 0. That's telling you when x is 0, when x is 1, y is 0. And notice if I look at my equation, replace the x with 1, you get negative 5 times 1, which is negative 5. You then add 5 to it, and you get 0. When x is 1, y is 0. And that's what that's telling us. So one way to find 3 other points is to pick some other numbers for x. I don't know. I got 0 for x. I got 1. Why not 2? Let's make x equal 2. And so I'll say y equals negative 5 times 2 plus 5. So when x is 2, y is going to be the same as negative 5 times 2, which is negative 10, plus 5 is negative 5. So when x is 2, y is negative 5. And I'll just draw that point. 2 comma negative 5. 2 comma negative 5. I got to make sure I look at the scale of my graph. That's right there. And I could keep doing that. I could just pick different numbers for x. I could pick 3 and replace x with 3, replace x with 4, replace x with 2.1 if I want. Or I can just realize that this equation here is what we call a linear equation, which means when I graph it, it always forms a perfectly straight line. So I don't actually have to use the equation just yet. I can just look at the 2 points I have and just draw other points that form the same line. For example, if I just continue the pattern, right here, and right here, and right here. All these points form the same line with the 2 points I gave, or up here. And notice if I make a mistake, let's say I make a mistake right here, you can kind of see it. One of my points is no longer in line with the rest of them. And so I didn't really need the equation to find 3 more points. I've already plotted, 6 more points. I could have used the equation, but ideally I also realize how I can just use the graph. If something is a line, and again, this is what we call a linear equation, right here. Any points you pick for x and then figure out the y values will always form a perfectly straight line. And since I already gave you 2, you didn't really need that. So now when I ask you to actually sketch the graph of the line, you may think I've done it already, or you may want to add some more points. And this is not wrong, as long as you realize I'm not done. Okay? Because this here assumes that I can only pick values of x that are whole numbers. I can pick any number I want for x. And so if I pick decimal values or rational values for x that aren't whole numbers, I'll still get points in here somewhere. They'll just be in between these. And keep in mind there's an infinite number of points I could pick, which means there's an infinite number of dots, which means, how do you show an infinite number of dots? Well, you just connect the dots. This is a solid line, and it goes on forever in both ways. So if I ask you to sketch the equation of y equals negative x plus 5, I need to show a solid line that goes on forever, not just a bunch of dots. And that is the equation. That is the graph of the equation of negative 5x plus 5. Now again, you may recall some things about how negative 5 is the slope and positive 5 is the y-intercept, but I don't need that yet. And so lastly, determine the missing coordinates here for the same equation, okay, where y equals negative 5x plus 5. All right, so for the first equation, I know the x coordinate is negative 8.2. I don't know the y coordinate. So how do I figure out that y coordinate?
Good afternoon, Fraser. Hi, if your staff is still working in the building, the janitorial team will be wrapping up the building at about 3:30. So if you could try to be out by then, or let Rick know if you're hoping to stay later, we very much appreciate that. Thank you.
Aren't you glad to have heard that? So I know the x value. I don't know the y value. Okay, and so how do I figure that out? Well, now this is the first time I really need that equation. And so I'm just going to go back to that equation and replace the x with negative 8.2. And so y equals negative 5 times negative 8.2 plus 5. And now on the right-hand side of my equation, I can just calculate that in a calculator. Negative 5 times negative 8.2 plus 5. And that will be my y coordinate. And I get 46. So when x is negative 8.2, the y coordinate is 46. And so I can do the same idea for the other one, except for the other final example, I don't know x, I do know y. But same idea. I can go back to my equation, and I know that y is negative 9, so I'll say negative 9 equals negative 5. I don't know the x yet. I will know it soon. And now I can solve for x. And so in this case, it's a relatively simple equation compared to some that we've done. I'm going to start by subtracting 5 from both sides. Negative 9 take away 5 is negative 14, which all equals negative 5x. And so to find that missing x coordinate, all I have to do finally is divide both sides by negative 5. And since the question, it can be expressed, my answer is a decimal or a fraction. The most important thing I see is that negative 14 divided by negative 5 is a positive number. So x is going to be a positive value. If you decimalize it, you get 2.8. And I'll just leave it like that. My last question, I decimalized it. If you leave it as an improper fraction, well, it's just going to be 14 over 5, which is positive, because the two negatives cancel out. And so notice by the end, it started coming back to solving equations again, even though the focus of this was a bit different. The homework for this, again, is from the MathLinks 9 textbook, which again, you should have given back. But I've scanned it online on the Teams page. And so you want to look at the scan pages. You want to look at pages 202 to 203, questions 4 to 7, and 10 to 12. Again, there's some tough questions there. And so give yourself some time. And that's all.